I'm a little uncertain about this talk because it's the topological content is close to 0. I thought I'd just tell you a little bit about the world of non-discrete groups, some of the representation theories surrounding the Baum-Connes conjecture as it applies to Lie groups and p-adic groups. Actually, I think I will talk almost exclusively about p-adic groups. And the reason is that I think that's much closer to topology and geometry, oddly enough, than Lie groups. What I'm doing for a living these days is thinking about Lie groups and exactly the things I'm going to talk about, but in the Lie theoretic or the real context. The reason I'm not going to speak about the subject that I actually know about is that it's there's very high analytic content. Whereas what I'm going to talk about is not analytic at all. There's a certain amount of Noetherian algebra which is involved, and a lot of geometry, but really no analysis whatsoever. I think that will bring the topic closer to your hearts than if I were to give lots of differential equations and so on. So I want to try to convince you that it's worthwhile to study p-adic groups, even if you're a topologist, even if your interest is in the Farrell-Jones conjecture and in machinery. I think there are some very interesting questions that as soon as you start to look at p-adic groups, what you find are projective modules all over the place. So maybe K-theory rather than L-theory is the relevant thing here. Projective modules coming from different sources. This is really what I want to explain today. And then it's a puzzle to organize all of these projective modules, like you do in K-theory, into some coherent picture. I should say that I've been thinking about this. I gave up thinking about this a long time ago, but I started thinking about this. Gosh, I don't even want to think about how long ago it was, maybe 20 years ago. And my conclusion is that it's really hard. And so I don't think there's anything just ripe for the picking here, some easy result just that you can steal. But I'm hoping that the sophisticated people with the big machines, a lot of geometric experience with the arguments that go into Farrell-Jones can say something intelligent in contexts where I and my co-workers could say nothing. So it's a hard problem. I think it's very interesting and challenging. Certainly even incremental progress would be welcomed by the experts in p-adic groups. Okay, so let's see if you guys can help out the representation theorists. Okay, so the whole point today is to talk about non-discrete groups. And there are, as I said, there are two classes that I might talk about. You could certainly study Lie groups. By the way, I'm not going to go too crazy. These are all going to be locally compact Hausdorff groups. But what I want to focus on are these totally disconnected groups to stay away from differential equations. So we'll take a look at these and leave the Lie groups to one side, except for possible comments. So let me just give you the 1-minute course in general, totally disconnected groups, just to give you a sense of what's involved in these things. First of all, they have lots and lots and lots of small subgroups. So every neighborhood of the identity in G contains a subgroup. Let's make it non-trivial by insisting that it's an open subgroup. No matter how small the neighborhood is, there's a little open subgroup even smaller inside of it. So there are lots of small subgroups in the language of people who study structures of groups. And that's the fundamental thing about these. The other thing that's worth pointing out is that if G is compact, then you can improve this statement a little bit and you can make the little subgroup normal. Can be chosen to be normal. So the compact groups in this totally disconnected world are very easy. They're pro-finite. Very simple structure. I'm going to be talking about representations of these groups in as linear representations on complex vector spaces. And what you find in the world of Lie groups, which are the automorphism groups of at least finite dimensional complex vector spaces, what you find is that there are no small subgroups. That's a famous fact, that every Lie group has a neighborhood of the identity which doesn't contain any subgroup at all, apart from the identity. And so what you see is that the representation theory of this group, which is going to be relevant to us, is going to be the representations, it's going to consist of the representations which factor through finite quotients. So one of the things you see right away is that representation theory will involve representation theory of finite groups. These finite groups involve fields of finite order, and they also involve more complicated objects. Let's just bundle it up and say arithmetic. It's going to involve lots of complicated questions. Let's agree we don't want to answer those questions. So there's going to be a component of representation theory which we should not be too optimistic to speak about, which is this very arithmetical component of representation theory. People know a great deal, but those people are not topologists, nor are they analysts. They're a different species. And so we'll try and set that to one side and try to understand what's left. Unfortunately, there is a very interesting and rich other part to the representation theory. It's something that we can understand as non-arithmeticians, and that's what I want to talk about. All right. People do, in fact, attempt to study arbitrary, totally disconnected groups, but that's not my ambition here. I want to look at particular examples coming, which are matrix groups. Suppose you start off with what people call a local field. So what it means is that just a field with a locally compact second countable topology. If you have such a thing, then it's comes automatically with a canonical homomorphism to the positive reals, and it's just defined in this way. Pick a Haar measure, which you're allowed to do because the thing is locally compact. I mean a Haar measure for the additive group underlying the field. And let's just multiply set by E. According to the uniqueness theorem for Haar measure, if I pick a Haar measure mu and I start to measure the size of sets E, then the dilations of these sets are going to be related to the undilated sets by some character here. So there's some canonical character floating around, which is called the norm. And these fields tend to have, in fact, do have a rather simple structure. So let's assume that the range of this thing is discrete. If the range is continuous, that you can study too, but those fields are just the real and complex numbers. These are commutative fields I'm talking about. In that situation, something rather nice happens. You can look at all of those elements in the field. I guess I should include 0 in this, with the property that their norms are less than or equal to 1. So this is now an open compact inside of G ring, inside of F ring, in F, or subring. Okay. And it has a very simple structure. If you pick an element which is whose norm is as large as possible, subject to it being less than 1, so P now is in O, then the principal ideal generated by it is a maximal ideal, is in fact the unique maximal ideal inside of O. So you have this very, very simple structure, and the quotient, of course, is a field with a certain finite number of elements. And the groups that I'm talking about, you just build out of this information. Maybe we'll just continue down here. Just matrices over F, or maybe matrices with determinant 1 over F. And they have lots of compact subgroups, and you can see at least one of them right away. Namely this. And if you want to build a smaller one, that's not hard too. What should we call it? K sub n. We could just look at all matrices which are equal to the identity modulo a very high power of this element P. Okay. Oh, sorry. Oh. And then it's a very small compact subgroup, in fact, so these guys get smaller and smaller and smaller, and the intersection of them is just the identity. So there you go. As guaranteed by the general theory, lots and lots of small subgroups. Of course, these are all normal inside of GLN of O. Okay, so these are the things we want to study. I want to tell you about. Maybe you don't want to study them, but these are the things that I'm going to tell you about. And so people study the representation theory of these groups, and the reason that it's interesting to study convolution algebras, projective modules, and so on over convolution algebras is precisely because of the links to representation theory. This subject is actually fairly old. When people started to study the representations of Lie groups, people like Harish-Chandra started to study the representations of Lie groups, there were other people studying, not Harish-Chandra until much later, but other people studying the representations of the groups that are under discussion here. And what was discovered is that this representation theory, modulo the arithmetic, which is up there, modulo the arithmetic, the representation theory is amazingly tractable. There's a beautiful geometric foundation to the representation theory, and on top of that there is some arithmetic, and so the arithmetic we're not going to say too much about except in the most general terms. On the other hand, it's still very interesting to come to terms with the geometry of the situation. So what people, after some experimentation, decided are the right representations to think of are what are called the smooth representations. So these are representations throughout. We're going to be talking about representations on complex vector spaces. And what it means, of course, it's just a representation, first of all. And it's a totally disconnected space. So smooth doesn't mean you start to take derivatives. That wouldn't be a good idea at all. What it means is that the isotropy groups of every vector is open. Is an open subgroup, not the identity, but some small, possibly small, open subgroup. And so come to an example, well, trivial representation as an example. I'll make a more interesting example in just a moment. In connection with this, people study the following ring. So this is the ring whose, for example, algebraic K theory or some other variant L theory might be, it might be relevant to study it. And here's what it is. is just functions on the group. Complex valued functions, because we're talking about complex representations. And two conditions. First of all, the functions should be compactly supported. And secondly, they should be smooth means, in this context, locally constant. And I want to think of this as an algebra. Of course, it's an algebra under pointwise multiplication. That's not so interesting. It's an algebra under convolution multiplication. So this is some analog of the group ring of a finite, not a finite, but a discrete group. And this is the thing we want to study. Anyway, so to study the representations of G, I mean these smooth representations, is exactly the same thing as to study non-degenerate modules of this Hecke algebra. These are equivalent, in fact, isomorphic categories. Okay. And so we'd like to know, can we, as non-arithmeticians, say anything about these things? And let's just examine that question. So I want to describe two theorems, both of them due to Joseph Bernstein, representation theorist, which give insight into the structure of this category of representations, or if you like, they give a lot of insight, a lot of information about the structure of this convolution algebra, which is not at all the sort of thing you can say about the convolution algebra of a discrete group, except in very, very simple cases. The punchline is going to be that as an algebra, this Hecke algebra, or if I gave it its name, it's the Hecke algebra, is not much more complicated than the group algebra of a free abelian group. This is the punchline. These things look very much like algebras of Laurent polynomials in a certain number of variables. That's the punchline. In fact, that's a little bit of an oversimplification, but that conveys the right idea. Okay, but first, let's maybe look at a simple example. Of a compact group. In Farrell-Jones land, you take the compact groups and more, and you just sort of, I don't know, you sort of scrunch them down to nothing. You don't bother to inquire about these, and these are the ones we certainly don't want to bother about because they have all of this arithmetic content. So let's deal with these rather quickly. Fortunately, it's very easy. Let's denote by G hat the dual of the group, so it's just the irreducible objects up to equivalence in this category of smooth representations. Each such representation basically is a representation of a finite group, according to what I said before. So it's going to be finite dimensional if it's irreducible. And what you're supposed to do is look at all of the endomorphisms of it, like that. If you have such an endomorphism, this is a device worked out by the ancients, I don't know, Frobenius, Schur, and so on. You can do the following thing. So if I have a T, maybe I should call it T sigma, belongs to, is a linear operator, just any linear operator, not equivariant or anything, just any linear operator on V sigma. You can manufacture, this is well known, a function on G out of it, and there's some normalization constant, which is a little bit interesting for reasons that you'll see in a moment. So we fixed a Haar measure, and there is some volume associated to it. And what you should do is take the trace of T sigma and then sigma of, I think, G inverse, like that. And the reason for the constant is that this is now an algebra homomorphism from each of these summands into here. In fact, each of these summands on the right, of course, is a complemented ideal in this direct sum, and these functions here commute in the sense of convolution multiplication, in fact annihilate one another in the sense of convolution multiplication. And so there's a algebra homomorphism from here to here. On the other hand, every representation is a module over H of G, so you can go in the reverse direction. Like that, and these are isomorphisms. So that's the representation theory of compact, totally disconnected, or really just finite groups in a nutshell. And what we see is that this algebra is not very interesting, except for the mysterious problem of understanding what this parameter space is. But we're not going to study that because that belongs to the world of arithmetic, especially in these examples. Okay. Let's consider a slightly more fancy example. Let's take a look at the groups that we're supposed to be interested in, wherever they were. There's the residue, GLNF, for example. Finally, we're in a position to study GL1. I mean, you have to start somewhere, so why not start with GL1? So this consists of invertible one-by-one matrices whose entries come from this ring of integers, in other words, just the invertibles inside of O, which is not a particularly simple thing, by the way, if you think about it. Oh, I didn't. Maybe I should just say. Of course, there's a famous example of one of these local fields, the p-adic numbers, and so P is equal to P, and the norm of P is the number P inverse, sorry for all of the P's there, and and the rational numbers are dense. This is a completion of the rational numbers, and this sort of characterizes what it is. And so you can work out what the integers are, and you can work out what the this GL1 group is, and it's quite complicated what it is. Anyway, what's left are just the powers of P, so this group actually factors in this way, a very simple way. We'll see this as a recurring theme. Okay, and so the Hecke algebra is just the Hecke algebra of this compact group tensor the Laurent polynomials. As for the Hecke algebra in this compact group, it's just a direct sum of copies of the complex numbers. One-dimensional irreducible representations account for those, and this is what you get. And there's the Laurent polynomials that I promised in the world's simplest example. And the theme is supposed to be that this is highly representative of what happens in general. Oh, I guess we can move over here. Take that back. If we were doing a proper course in this subject, the next thing to consider would be groups which are compact modulo their centers, and we would analyze those. This is an example of a group which is compact modulo its center, but I'll skip over that to try and maintain some kind of schedule and go directly in a different direction to non-compact groups, and just attempt to carry over. This is what we do in mathematics all the time. We have a successful theory here in compact groups, so we'll just attempt to steal from it and make some kind of theory over here in the world of non-compact groups. So you can't do anything about the group. It's non-compact. You can't make it into a compact group. On the other hand, you can attempt to define what it means for a representation to be compact, and it doesn't mean it's finite dimensional or anything like that. In fact, these groups do not have any finite dimensional, typically. If the group is not non-compact, do not have any finite dimensional irreducible representations. But what it means is that it's possible to emulate what you see here, at least to a certain extent. So we can take the endomorphisms of V sigma. Now this is an infinite dimensional vector space, perhaps, and I want to limit the number of endomorphisms I want to consider, because I want to, among other things, take the traces of them. I'm going to put here S, or I'll call it smooth here, maybe S later on. What I mean by smooth endomorphism is that, first of all, it has finite dimensional range. I want it to have finite dimensional range, then there won't be any problem in computing, not calculating, but understanding what this trace really means. And the other thing is the following. If G acts on V, then of course it acts on the endomorphisms by conjugating, and I want this to be a smooth vector in that representation in the sense of the definition which appears up there. So this is some subring of all endomorphisms. And I want it to be the case that when I apply this construction, don't worry about what this constant is, it's just some constant. In fact, you could just eliminate it for a moment. When you apply this construction, you end up over here. You'll certainly end up with a locally constant function if you're dealing with smooth endomorphisms. But the question is, will the function be compactly supported? That's you don't get for free, but let's just assume that it is, so that we obtain a map like this. And let's assume when we look at the action map, when you take the action map, you'll certainly get smooth vectors in the endomorphism ring. Let's assume they also have finite dimensional range. So we have some picture like this. If that's the case, then once you adjust, it's a rather beautiful fact that you can adjust this constant. You can choose a constant. So the role played by this dimension of the vector space over the volume, this is infinity over infinity. It's possible to choose a so-called formal dimension, which is a certain number, so that both of these are algebra homomorphisms, and the composition is the identity. In other words, this is a complemented ideal inside of here. This is a rather unusual circumstance, but it's a fact. At least if the center of G, if the center of G is large, if the center of G is not compact, it's easy to see there are no compact representations. We should talk about compact modulo center representations, but as long as the center is compact, then there are lots of these rather remarkable representations. And just to give you a clue that there's something potentially a little bit topological going on here, maybe I'll just try and squeeze it on the last line before we go up. Another interesting fact is that for a suitable Haar measure, so as you see in the compact case, these numbers depend on the choice of Haar measure. But if you choose the suitable Haar measure, of course it just means the only choice is multiplying by a positive constant. These formal dimensions are integers. So whenever something is an integer, there's the demand that there should be an explanation of why it's an integer. This is a theorem of Harish-Chandra. But this is the first thing that a topologist might attempt to understand, is why you actually get integers here. I think that's by itself not a trivial matter. Okay. I guess I didn't say why people want to study these. Of course, everyone has a right to study whatever he wants to, and that was why these things were studied initially, but they've acquired a new life, as you know, thanks to the Langlands program. So this remains a very difficult and interesting subject. As you can imagine, the major outstanding issue is the arithmetic issue that I was mentioning before. Okay. Everything that I'm telling you about was proved by Bernstein a long time ago in the 1980s. All right, but it begins to be a little bit interesting. It's unexpected that you could do something like this for an interesting group. In fact, you can do it all the time, very frequently, at least if the center is compact. Okay. Maybe I should just make a remark. I don't want to, out of concern about time, say too much about this. Inside of every p-adic group, every one of these groups that we're discussing, like these guys here, actually the definition I'm about to give, you could make in complete generality. There is a subgroup called circle G, which is just the group generated by compact open subgroups. So it's normal. It's a normal subgroup, obviously. And now so you can divide and you can ask what the quotient is. And the quotient turns out always in this world of reductive groups like these guys. So these are examples of reductive algebraic groups. There's always a lattice, a free abelian group, finite rank. Okay. And inside of this, there's some sublattice, a finite index. This is not canonical, but it always exists. Such that this sublattice lifts to G, and it actually lifts centrally inside of G. And so inside of G, we have just a lattice times this circle group, and as a finite index subgroup. Maybe I should say in this context that lambda lies in the center of G. So if a group happens to have a center like GLN does, then it's not a terribly difficult matter to analyze what's going on, because there's always a group without a center, or rather with a compact center. So yeah, that's I guess what I wanted to say here, and I forgot to. It's a fact that the center of this fellow is compact. So that the group splits in this way. There are lots of tori, lots of free abelian groups floating around, and modulo some small virtual issues of groups of finite index. This is the picture, normal subgroups of finite index. This is the picture. Okay. These reductive groups, yeah. So this language is used by some people, like Bernstein, but these are what the representation. There's a theorem which identifies these with what are called supercuspidal representations. Maybe I'll mention that in a little while. There's a type of representation which is not just irreducible in the sense of representation theory, but not subject to analysis in terms of smaller subgroups and using induction and so on. And the ones which irreducible representations which cannot be simplified in any way whatsoever are called the supercuspidal representations. And it's a theorem that every supercuspidal representation is either compact or compact mod center in this situation here. Okay, so in just putting these two bits together in place of the smooth, representations on a vector space. What this looks like, by the way, I guess I should say, as an algebra, this is just M infinity of C. The infinite by infinite matrices with only finitely many non-zero elements. The right thing to use in place of this is exactly what you might expect, which is this. Here's the group algebra of this lattice. Think of this as a representation of G, and now just tensor it with the endomorphisms of, maybe I'll call it circle, V circle sigma. This is now a compact representation of the circle group. Okay. And there's a beautiful theorem of Bernstein, which, I forgot to mention that there's a small element to check here, but I'll just mention it here. Let me go back to this compact situation. So let's just assume that we're just studying the compact representations. I meant to mention this before, but I didn't. You can split off each one of these compact representations one at a time, and it produces a copy inside of the Hecker algebra of just M infinity, which is no stranger to us. This is a very easy ring to understand. In fact, you can split them all off at once. I'm just writing it for economy here for compact representations, but the same thing is true for compact modular center representations. So the totality of all of these representations, the totality of all of these ideals, the direct sum of all of these ideals, is itself a complemented ideal. It just falls off like that. There's such a picture as this. The fact that the Hecke algebra acts on the maps into the direct sum, not the direct product, is highly non-trivial. Okay, the Hecke algebra is acting. Each of these is an H of G module, and it's a little unusual that you would have such a picture as this, but you do. This is a famous theorem of Joseph called the uniform admissibility theorem. And it's not trivial, and the reason I mention it is that it's very closely related to, it's not much of a sentence, to the following statement. Suppose you take this Hecke algebra, the very algebra we've been talking about, and look inside of it. So the functions in this Hecke algebra are supposed to be locally constant, but suppose we fix a, so to speak, modulus of local constantness. We pick a compact open subgroup, not the maximum one, possibly a very, very small one, and study functions which are only which are constant on k cosets, as indicated, k double cosets. Then this thing here turns out to be a Noetherian ring, Noetherian complex algebra. So that we're in a very, very tame and simple world here, surprisingly. I mention that because I want to discuss the other theorem of Bernstein. So this algebra is quite easy to understand. There are lots of, according to what I just said down here, lots of interesting projective modules to take account of. Namely, each of these compact representations is a projective module in the situation of a group with no compact center. There it is up there. If you, so to speak, combine all of the compact representations with some twists coming from the center, you form this thing here. Nope. What am I wanting to look at? Oh yeah, all the way up there. If you form this group algebra tensor V sigma, that also is a projective representation, a projective module. So wherever you look, projective modules, and the situation gets just only better thanks to the following construction. Which I have to speak quickly about. Gosh, time flies. Okay. Although there are many, or always many, compact representations, this is far from everything. Fortunately, there's a complete accounting of where to look for all of the other representations, which is through a method of induction, as you might expect in representation theory. And what you induce from are what are called parabolic subgroups, and these are defined in a way which is sort of pleasingly dynamical. You just fix an element in G. Oopsie. And then just look at those elements in G with the property that when you conjugate them by this element A, what you get is a family of elements. So let's just fix one direction here. Oops, hang on. This is going to look horrible. This set here is pretty compact. So the sequence of conjugates don't wander off to infinity. They just wander around in a bounded part of the group G, at least in one direction here. These groups always come in pairs because you can do exactly the same thing with negative numbers. These are parabolic subgroups, and they're given in some very dynamical way, and sitting inside of them, in fact as normal subgroups, are groups n, which are worth thinking about just briefly. So it's just a set of elements such that a to the n, g, a to the minus n doesn't just remain bounded. In fact, this converges to the identity. Okay, and the same thing for n bar. Okay. Let me just draw a little picture, my favorite picture, to help you understand why these subgroups are so important. It's a cartoon. But it's here's the picture I want to draw. So here's a cone inside of a quadric. The quadric is the group SL2, one of the groups we're trying to understand, perhaps. And inside of it, there's a cone which is asymptotic to this, which is just AD minus BC is equal to 0. Which is a good model for G at infinity. Of course, this is the real picture. And you can figure out what this space is. I forgot to say what L is. It's exactly explainable in terms of these dynamical subgroups, N and N bar. L, by the way, so each group P has a semi-direct decomposition like this. So L is the intersection of P and P bar. That makes our L. And so I just mentioned this picture to show you that these groups have a very dynamical and simple geometric aspect to their existence. It's not capricious to study what these groups really are. So for example, in this case, these unipotent groups tend to look like this. I'll leave to you as an exercise the problem of figuring out what A should be. And of course, L is the diagonal matrices. Like that. Okay. And, next I can lift this up. Now let me tell you the amazing theorem of Bernstein, which in a certain sense completes the geometric description of the Hecke algebra, and at the same time provides us with a huge additional supply of projective modules. If I have a representation of L, a module over L, smooth representation, I can produce, M means module over the Hecke algebra of G by an operation called parabolic induction, depending on P. And you go in two steps. The first is that if you have an L module, well, L is a quotient of P, because n is a normal, wherever it is, n is a normal subgroup of P, and so there's a group homomorphism from here to here. So each time I have an L module, H of L module, I'll have an H of P module. Now I have a representation of P, so I do ordinary induction like you do, and I get a representation of G. And the famous theorem of Bernstein is that this parabolic induction has a right. It's not so impressive, but it also has a left adjoint. The key thing is the right adjoint. The two adjoints, by the way, are essentially the same. The left and the right functors are not the same, but essentially the same. So these functors are exact on left exact and right exact, as you see, and same for their adjoints. So parabolic induction sends, in fact, finitely generated projective modules to the same. Okay. And from this theorem, it's a short step to complete some sort of preliminary description of what this ring H of G is. It contains many matrix subrings as complemented ideals. The rest is also decomposable like this. And what each of these summands is just Laurent polynomials. Oh, I shouldn't say is all of them, but these are subrings, large subrings in Laurent polynomials with matrix entry as coefficients. So what the Hecke algebra looks like, in complete contrast to what you see in discrete groups, is a bunch of M infinities. These are the things you start with. And then Laurent polynomials in one variable, whose coefficients are not scalars, they're infinite by infinite matrices, M infinity matrices. Maybe not the full Laurent algebra of such Laurent polynomials. For example, at some point, it might be the case. So such a Laurent polynomial, of course, is a function from C cross into matrices, and you might have to require that at a certain point the matrices be diagonal with respect to some decomposition of the matrix space. And then the same thing with Laurent polynomials in 2 variables and 3 variables and so on. That's what this thing looks like, up to some maximum number of variables. It's very, very simple. It's completely unlike what you see for discrete group rings, which typically have no discernible interior structure whatsoever. These things are amazingly tractable, and you can see with your own eyes, once you believe in Bernstein's theorem, that there are many, many projective modules that demand some kind of bookkeeping, some kind of explanation. That's what you guys are supposed to know about. Okay, let me just I want to say one more thing. Can't remember what I want to say. I'll leave that space. Maybe it'll come back to me. Okay. I'm sorry, can you say that again? Sure. Oh, I was pointing at the wrong thing. Yeah. Let me try to. So first of all, yeah, there's some sort of division line here. This decomposition of the Hecke algebra, or equivalently the decomposition of the category of smooth representations, is basically a very short step away from this fundamental theorem of Bernstein, which is also a theorem which provides us with all of these projective modules. And so this theorem allows us to say that we can sort of understand what this thing is. Against all expectations, it looks like Laurent polynomials, again and again and again, the direct sum of a whole bunch of things like that, with some strange conditions on the matrix entries at maybe certain points or certain subvarieties in a torus. That's all I wanted to say about that. Did that help? Ah. Yeah, so this is, thank you very much. The square brackets means that there's some equivalence relation, which I'm not going to tell you about. Anyway, these are equivalence classes of compact representations of the of these groups circle L. So each L is a reductive group in its own right, block diagonal matrices. It has a circle L subgroup, just like we had circle G before. And this means equivalence classes according to a very easy and explicit equivalence relation, which I'm nonetheless not going to tell you about. Okay. It's easy to describe what the index set is in abstract terms. What's extremely difficult is to parameterize this, because if you want to parameterize this, it comes down to matters of arithmetic. You need to parameterize the smooth representations, and that's much harder than parameterizing the irreducible representations of these compact matrix groups, which is already an incredibly hard topic. So there's, okay, it's not a trivial matter by any means. All right. But let me try and, having spent nearly all my time explaining that this Hecke algebra has a sort of interior, this is like the group ring of a discrete group, the sort of thing that you plug into some machine, but it has an internal life. You know, it's interesting in its own right, in a way that complex group rings or integral group rings seldom are, because you just can't say anything about them. But these fellows here have this amazing, when you start to think about it and you talk to Bernstein, you see these have an amazing personality. I remembered what I wanted to say. Yeah, just quickly about the proof. Which I think is a little bit inspiring. This proof is not an easy thing to come about, because it really is, of course you can see from the picture, it's pretty much, it will pretty much imply that this Noetherian property, but if you take this for granted, then there's not much to the proof beyond this Noetherian condition and the sort of geometry which is summarized in this picture here. This is pointed out by Bezrekavnikov and Kashdan. It's a beautiful paper. So if you're willing to take on faith this Noetherian property, which I recommend, then this proof is purely geometric, and it has something to do with this asymptotic relation between these two spaces. So here's G itself, of course. It's within the realm of possibility that people like me, us, can understand what's going on as long as we take this Noetherian property for granted. This Noetherian property is much, much harder. Unfortunately, it's related, as I said before, to this uniform admissibility that you see up there. Easy to sort of package, but difficult to understand in other terms. Gosh, let me try and say at least something about something more geometrical. I've tried to explain something about what you might call the right-hand side of the conjecture. I've tried to explain that if you have a p-adic group, you know, the SL3 of QP, something like that, then you can say a great deal about what the group ring is in a way which is unavailable for discrete groups. And by the way, it's the same for C-star algebras as it is for anything else. We don't know anything about what the C-star algebra of a discrete group is any more than we understand what the group ring of a discrete group is. Well, we have results, but they all say the C-star algebra of a discrete group is terrible. And then another theorem, it's terrible in a different way. All of our results say that it's terrible, not good. All right. So on the one side of any of these isomorphism conjectures is some sort of algebraic invariant built out of some group algebra, and on the other side is one of these universal spaces. And the one I want to discuss here is the one for, because it's the one that I understand, and it's the one that comes up in the C-star algebra isomorphism conjecture, the universal space for proper actions of G. Because this has a beautiful picture, a bit beautiful theory surrounding it all by itself. Let's just take a reasonably substantial example. Take SL3, one of these p-adic fields. So I mentioned before a certain compact open subgroup, the SL3 of the p-adic integers, like this. It's not the only one. It's not the case inside these groups that there's a unique maximal compact subgroup, which is the story for Lie groups, but it's not the case here, because here's another one. If I conjugate this fellow by the matrix, which is this matrix. This is a matrix whose determinant is P, not 1, so it's not in SL3. Then I'll get a genuinely different compact open subgroup, which is not conjugate to the one that I started with. And there's one more to consider. If I conjugate with this invertible 3x3 matrix, I'll get yet another genuinely distinct compact open subgroup, but that's it. Any maximal compact open subgroup is conjugate to one of these fellows here, and you should think of them as sitting in a little triangle like this. Here's K0, here's K1, here's K2, and it's of interest to study the intersection, which you can easily figure out what it is, and the same thing here, and the same thing here. And for that matter, it's of interest to study the triple intersection like that. And now what you have is a little triangle of groups, if you like. Think of this as a solid triangle. And this space E bar G is the following thing. It's called the building, the affine building. So it's, in this particular case, a simplicial complex. Usually it's a polysimplicial complex, but here just a plain old simplicial complex. And the vertices are just like I've drawn them. G has to act, so I need and it has to act properly. I'm going to need more than 3 vertices. Well, I'll just take the union of the coset spaces. Shall I call them Gj, like this? So there's 3 homogeneous spaces, discrete, because Kj is open, and those are the vertices and the edges, just the union over all the pairs Ij of G and Kij. So there's 3 disjoint unions here, a disjoint union of 3 homogeneous spaces, and finally the 2-dimensional faces is just G modulo. I guess I can just call it K1, 0, 1, 2, like that. And these are glued together by inclusion. Think of this as a set of cosets, and this is a set of cosets, and sometimes one of these, well, always one of these cosets is going to be contained in some cosets up here, and those give the incidence relations, and they tell you how to join all of these things together to give a rather interesting simplicial complex. And if we were down talking about SL2 instead of SL3, you would get a tree like this. Here you get a 2-dimensional version of a tree, the affine building. Okay. So it's very simple and a beautiful object. So this is, in a natural way, a cat-0 space in the standard metric that you put onto a simplicial complex. It's cat-0, globally cat-0. And so it's an example of this universal space that I was mentioning. And it's time to finish, so let me wrap this up. Yeah. The left-hand side. The left-hand side of the assembly map, if you like, what you get by starting with the right-hand side and disassembling, is, well, rationally, the same thing as the homology of the following complex. At the bottom, I'll just put the representation rings of these finite groups, compact profinite groups. And here I'll put the representation rings of the edge groups, and here the representation ring of the face group, like that. And what are the boundary maps? Well, we have a little triangle. There it is. So there are simplicial boundary maps involved that you can easily work out that need to be put here. On the other hand, we also have to do something with the coefficients because the group changes from here to here. And what we do is just induction. After all, each Kij is a subgroup of Kj and Ki. So this is a combination of the simplicial boundary and induction. And it's very concrete, but it's completely different than what you see over here. So let me just tell you 2 problems which seem to be rather paramount in this whole thing. The first is sort of obvious: to account for all of Bernstein's projectives. For the Hecke algebra, so Bernstein guarantees that the Hecke algebra has all sorts of projective modules. Where do they come from? Well, according to the isomorphism conjecture, they come from this complex. But how do they come from this complex? The fact is that nobody knows. This is what we call chamber homology, so chamber complex. Oops. a lot of interesting geometry going on. There's the geometry of the building. There's the geometry, it's now disappeared, of this approximation. You can still see a ghost of it up there. I should say that at infinity, in this approximation space, the one that you see up there, at infinity are homogeneous spaces, and they look like G modulo P, the very same parabolic subgroups that appear in parabolic induction. So there's a lot of interesting dynamics involved on the group itself. On the other hand, there's interesting geometry on the building. It's a beautiful cat zero space. Okay, and now we know nothing about this. And here's another problem we don't know anything about, also about decompose chamber homology. In our younger days, I was working on this with Paul Baum when he was younger, and Roger Plyman. We thought there should be some actual decomposition of this complex. That doesn't seem to be the case. But anyway, decomposed chamber homology according to the Bernstein decomposition of the Heck algebra. All of those Laurent polynomial rings that I was mentioning before. The assembly conjecture, at least the one that we've so far formulated, the one for C-star algebras, it's not just a conjecture, it's a theorem. And so there is such an isomorphism. It follows such a decomposition. It follows from the theorem. But to understand this geometrically a priori, to be able to say something a little more than what I just said, there is a decomposition, is amazingly difficult. We had a period when we were corresponding with the p-adic experts, and on the basis of this correspondence, we made predictions. You take a representation here. Okay, you want to, and maybe you've constructed a cycle for chamber homology. Now you want to deal it out according to the different Bernstein components, and so you can guess how it should go according to, in certain cases, for example, GLN, according to representation theory. And so we'd send our guesses to the p-adic people. They got irritated after a while because all of our guesses were always correct, but we don't know why they're correct. There's a lot of interesting arithmetic which goes into this, which of course we're not experts to understand, but we don't even understand these very fundamental problems, let alone the knowing how to do the underlying computations. So this is the background of the left-hand side and the right-hand side, and okay, it's your job to understand why they are the same. So thank you. Sorry, which SL3 you mean? And what do you mean by simple? Yeah. There is, even for SL2, it's not simple. There are subtleties even for SL2. Yeah, when you deal with SL2, it becomes relevant to study all of the tori, compact tori inside of SL2. And how many compact tori there are depends on arithmetic. It depends on what, for example, if it's SL2QP, it depends on what the prime P is. Not much. 2 is special and the others aren't special. But this is typically the case that for low values of the prime it's extremely difficult, and then for higher values it's just difficult. This is not easy for SL3. I believe it to be the case even for GL3, which is easier than SL3. We do not have a complete, how to say it, basis for this chamber homology in terms of concrete cycles. We here means Roger Plyman and his p-adic collaborators, real experts in this world, don't understand how to write down an integral basis, if you like, for these homology groups. So it's not trivial at all if you attack this the wrong way. One hopes to avoid those complications, which of course appear on both sides of the conjecture. One hopes to avoid those two complications by making some statement which just says the complications are over here are exactly the same as the complications over here. We know exactly how to do that for real groups. That's this Mackey business that I think I've talked about here before. But for p-adic groups, we have no understanding about what to do. Yeah. Oh, excuse me. This is the representation. This is a free abelian group generated by the irreducible representations of the group K. I mean irreducible smooth representations, and so they're irreducible finite dimensional representations. That's the same thing. Okay. Yeah. That's correct, yeah. No. No, we don't even see that. We don't even understand how to deal the generators of chamber homology according to the, the associate class of the parabolic. We don't even understand that. Pathetic, isn't it? But that's the way it is. Thank you.